In this video, we are going to do some problems. So far in the course, we have studied rings, definition of rings, examples of rings, homomorphism of rings, and then I introduced ideals. So, to learn this subject very well, you have to do lots and lots of problems. So, let us start with some problems today. I will try to explain in detail how to solve these problems. So, this will hopefully help you understand the material much better. So, today's video is about problems. Okay. So, let us start with something about definition of rings. So, let us say the question is determine which of the following are rings. Okay. So, I will give you some sets and we will decide if they are rings or not. So, let us look at the following set A plus IB, where A and B are integers. So, actually this is a subring of C, right. So, I remember is the square root of minus 1. So, I is an imaginary complex number. I am looking at A plus IB where A and B are integers. So, in fact, this I have already discussed this example before. This is a ring, right, and let me quickly recall why, and then we will move on to the other problems. So, here the point is to check that the set is closed under products and sums, and there are inverses for addition, there is multiplicative identity and so on. So, if you obviously add two such things, you get A plus C, B plus D, right. This is certainly if A, B, C, D are integers, A plus C and B plus C, D are also integers. More interestingly, if you take the product of any arbitrary elements, you get AC minus BD plus I times AD plus BC. So, this is also in this set, if you call this R, R, okay. And I will let you to check, I will let you check the other conditions. Other conditions are easy to check also. Typically, the key things to check would be product and identity element and inverses. So, A plus, of course, identity element is there, it is 1, it is of the correct form. So, R is a ring, and remember it is called the Gaussian integers, ring of Gaussian integers. And it is denoted by Zi. So, this is a familiar ring to us. We will come back to this ring later in the video today. So, let us look at another ring. I will keep denoting all these by R. So, I think I called, yeah. So, this is the second ring. So, let us take A plus, now instead of I am going to take root 2, I will keep AB in Z again. Okay. So, this is in fact a subring of R now, right, subset of R. We have to still determine if it is a ring or not. So, I am taking real numbers of the form A plus B times root 2, where A and B are integers. So, is this a ring? So, again we can check easily that the sum is A plus C plus B plus D root 2. That is no problem, right, that is in R. So, let us check the product. So, A plus B root 2 times C plus D root 2. So, this would be, now root 2 times root 2 is 2. So, it will be AC plus BD times 2. So, that is AC plus 2 BD plus the root 2 term will be AD plus BC, right. This is also in R, and the other conditions are also easy. Okay, that I am going to leave for you. The crucial thing, as I said, is the product. So, R is a ring. We denote it just following the earlier notation. We put it Z square bracket root 2. Okay. So, let's now look at the following. So, here I will replace I and root 2 of the last two examples by 1 by 2. So, let us say a plus b by 2, a and b are inside. Okay. So, this is actually inside the rational numbers now, right, each of them is a rational number. Is this a ring? So, let us do the sum first. So, this is actually not a problem because it will be a plus c plus b plus d by 2, this is an R. So, this is okay, right. So, this is fine. What about the product? Okay. So, now actually we will run into some problems, because if you multiply these you get AC, AD by 2, BC by 2, so far no problem, but the next term will be BD by 4, right. Now, is this an element of R? Can you write this as a plus something, an integer plus another integer divided by 2. So, can this be written as some x plus y by 2 where, so is this equal to where x and y are integers? You certainly cannot, that is the point, because if you write it like this, the denominator will be 2 if you add them and write it as a single rational number, whereas denominator is 4 provided b and d are not going to cancel 2. So, for example, so this is not possible in general, I will write this is not possible in general. So, I am going to just illustrate. So, if you say that something does not happen or some property is not satisfied or something is not a ring, you have to give an example to show that that property fails in that particular example. So, example 1 by 2 is in R, right, because 1 by 2 is of the form 0 plus 1 by 2, but 1 by 2 squared, which is 1 by 4, is not in R, right. If R is a ring, 1 by 2 squared is supposed to be inside 1 by is inside on also inside 1 R, but 1 by 4 cannot be written as a plus b by 2, that is very easy to check. 1 by 4 is not in R, so R is not a ring. Okay. So, and this particular point I will leave for you as an exercise, it is not difficult to check. You suppose there is a and b with this property, a plus b by 2 is 1 by 4, you cancel, I mean you cross multiply and check that there is a problem, because one side will be divisible by 2, one side will be divisible by 4, and there is some contradiction that you will get. So, R is not a ring. So, this example shows that you have to be careful about taking whatever you want. If you take a plus bi in this example or a plus b root 2 in this example, you will be fine, but a plus b by 2 is not going to give you a ring. The difficulty in this third example was 1 by 2 times 1 by 2 is not inside this set again, whereas root 2 times root 2 is also is again in this set, I times I is again in this set. So, that is the difference in these 3 examples, between these 3 examples. Let us look at another example. So, if you think about it, all of these are actually, so this question is about if something is a ring, but they can also be considered as questions about subrings. So, I have given you subsets of well known rings. The first one is a subset of complex numbers, and the question is it a subring. The answer to that question and the question whether R is a ring or not is the same, because a subring is simply a ring with the same operations. So, here we are taking the same operations as the operations on C. Similarly, here R is a subset of R, it happens to be a subring of R. Here R is a subset of cube and it is not a subring of R. Now, let us look at, let us say, polynomial ring, right. So, this is polynomials in X with coefficients in R, right. So, these are real number polynomials, real polynomials in one variable called X. So, in this let us look at the subset of f of x in R x, degree of f of x is less than or equal to 3. Okay. So, here I am taking all polynomials whose degree is at most 3. For example, x cubed is in R, x power 4 is not in R, right. So, x power 4 has degree 4, so it cannot be inside R. Now, is this a ring? That is a question, right, and you can clearly see that it is not. It is not a ring. Why not? Because x is in R, but x power 4 is not in R, right. If R is a ring, it is supposed to be closed under addition. You have one element, if you multiply it with itself 4 times, it is supposed to be inside the set again, but it is not. So, it is not a ring. So, let us modify this. So, this is not a ring. What about I will modify inside still the polynomial ring over real numbers. Let us look at f x inside R x, degree of f x is at least 3. So, I am just inverting the inequality. So, here I am taking degree at least 3. Is this a ring? I claim this is also not a ring. Why not? There are several reasons why it is not a ring. I will give you 2 reasons. 1 is not in R prime, right, because what is the degree of 1? Remember, 1 is a constant polynomial, so its degree is 0. So, 1 is not in R prime. Also, it is not closed under addition. Another reason is if for example, x power 4 is in R prime, x power minus x power 4 plus x squared in R prime, but if you add these two, but what is the sum of these two? If you add these two, you get x squared, which is not in R, right. So, you see that it is not closed under addition also. So, it is not a ring. So, if you just arbitrarily say degree is at most something or at least something, it is not a ring. Okay, let us look at 2 more examples. So, E, let us look at the subset R consisting of rational numbers. So, A and B are integers and A by B is in Q. So, I am already implicitly assuming that A and B have no common factors. Okay, so, whenever you write an element of rational numbers, you cancel all common factors. 3 does not divide, let us say the condition is 3 does not divide B. This is the definition of R. So, for example, 1 by 2 is in R, right, 1 is in R because 1 is 1 by 1, right. So, 1 equals 1 by 1 because 3 does not divide 1. On the other hand, if you take let us say 2 by let us take 3 by 6, let us take 3 by 6, is it in R? So, if you think about it, 3 divides 6, so it looks like it is not in R, but remember before you can check whether 3 divides the denominator or not, you have to cancel the common factors. So, you cancel common factors, 1 by 2 is what you get, and then 3 does not divide the denominator. So, it is in R. So, you have to check whether 3 divides the denominator or not after you cancel the common factor of numerator and denominator, and after you cancel the common factors, if 3 does not divide the denominator, it is there, if 3 divides the denominator, it is not there. Okay. So, I hope the set is clear. So, the set is this, it has 1 there, it also has 0, right, because 0 can be thought of as 0 by 1. So, 0 is also there. Now, is this a ring? That is a question. So, to check this, let us check actually the conditions for a ring. So, remember again the question whether this is a ring or not, is same as the question whether this is a subring of Q or not. So, it has 0 and 1. Now, let us take two elements in R. Okay. So, let us consider their sum and see if it is also in R. What is A by B plus C by D? It is AD plus BC divided by BD. Now, is this in R? Right. We know A by B and B C by D are in R. So, now this condition implies 3 does not divide B, 3 does not divide D also by definition, right. 3 does not divide B, 3 does not divide D, because A by B, C by D in their simple forms after cancelling common factors are in R. So, 3 does not divide B and D, but because 3 is a prime number, this implies 3 does not divide the product also. See, this is the property of prime numbers. If 3 is a prime number, it does not divide B and D, that means 3 does not divide BD also. Now, let us look at the sum. Now, I know that in this form 3 does not divide the denominator, but of course, it is possible that it is not in its simplest form, meaning there might be common factors between AD plus BC and BD, but does not matter, because if you cancel the common factors, what you will get in the denominator is something which is the divisor of BD. BD itself is not divisible by 3. So, after cancelling common factors, it will retain that property, right. So, 3 will not divide whatever is the denominator after you cancel the common factors. So, in other words, AD plus BC by BD is in R, right. So, the answer to this question is yes. Okay, just to recap again, 3 does not divide B and D. So, 3 does not divide the product BD, here 3 is a prime is used, and after cancelling common factors of this quotient AD plus BC by BD, whatever is a new denominator being a factor of BD will continue to be not divisible by 3. Okay, so, this is not a multiple of 3. So, A by B plus C by D is in R, that is good. So, R is closed under addition. R is closed under addition. So, now let us look at product, is it closed under multiplication. So, let us again take A by B, C by D in R. Now, let us take A by B times C by D. So, this is AC by BD for the same reason as before. So, here also the denominator is BD, which is not divisible by 3, and after cancelling common factors, what you get is still not divisible by 3. So, AC by BD is in R. So, once you checked these conditions, of course, if A by B is in R, minus A by B is also in R. Okay. So, that is also seen by taking the using the closure under multiplication property, because minus 1 is there, the product is minus 1 times A by B, which is minus AB is in R. So, we have checked all the conditions. Remember, associativity of addition multiplication, distributive property of addition multiplication are automatically true, because this is sitting inside Q, which has all the required properties. So, R is a ring, right. So, R is a ring. So, I hope this example is clear, and to clarify this a little more, let us modify this slightly and I will call this R prime. So, I will take as before A by B in Q, but instead of saying 3 does not divide B, I will say 4 does not divide B. Okay. So, here I will say 4 does not divide B after you cancel common factors. So, this is not a ring, I claim, because 1 by 2 is in R prime, right, in its simplest form, which 1 by 2 is in already simplest form. 4 does not divide 2. So, 1 by 2 is in R prime, but if you take 1 by 2 squared, you get 1 by 4, and 1 by 2 is also in its simplest form, and 4 does divide R prime. So, it is not 4 does divide 4. So, 1 by 4 is not in R prime. So, R prime is not a ring. So, again because I said 3 does not divide B, I got a ring where, and because 3 is a prime. So, I will end this by simply saying define, let us say R sub P to be A by B in Q, P does not divide B. Okay. So, here P is an integer. So, I claim that, actually let us write it like R n, okay. N sorry, P B is here, this is n. So, let us define R n to be all rational numbers where n does not divide B. So, here R n is a ring, I claim if and only if n is a prime number. You can prove this as an exercise. Using the ideas in this problem, you can prove this. I have given you one example, 2 examples of R n when n equal to 3 and 4, say R prime is R 4, right, in my notation now, and here R is R 3. So, R 3 was a ring, we checked, R 4 was not a ring, we checked. So, now I am asking you to prove the general statement R n is a ring if and only if n is a prime number. So, exactly the same idea, if n is not a prime number, it is a product of 2 numbers, and then you can use what I have done here for 1 by 2 to show that R n is not a ring. If n is a prime number, use the problem about R 3 to prove this. So, this is a good exercise for you to do. Okay. So, let us do one more final thing about whether something is a ring or not. So, this is F. Let us look at R now to be rational numbers of this form. So, I am taking rational numbers. So, A is any integer and n is a natural number. So, I am taking a rational numbers of the form A by 2 power n. So, denominator must be a power of 2, in other words. So, for example, 0 which is 0 by 1 which is 0 by 2 power 0 is in R. Similarly, 1 which is 1 by 1 which is 1 by 2 power 0 is in R. 1 by 2 is of course in R, right. 3 by 2 is also in R, 3 by 4 is in R, and 1 by 16 is in R. So, these are all elements of R. On the other hand, 1 by 3 is not in R, 1 by 6 is not in R, right, 8 by 10 is not in R, and so on. So, these are elements of R, these are not in R. So, again the test is very clear, to be in R in the simplest form. So, of course, again I have to simplify. So, 8 by 10, so this, let us cancel the common factors here. So, you had 4 by 5, right. So, after you cancel the common factors, what remains, denominator of what remains should be a power of 2. So, is this a ring? So, that is the question, is this a ring? So, we already checked that 1 is there and 0 is there. So, let us check closure under addition and multiplication. So, you have A by 2 power n, let us say, and B by 2 power m. If you take the product, it will be A times 2 power m plus B times 2 power n divided by 2 power m plus n plus m, right, because that is 2 power n times 2 power m. Now, is that in the correct form? Yes, it is. Again, as before, it is possible that this is not in the simplest form, but you can cancel the common factors. Only factor of denominator is 2. If you cancel some of those factors, you will remain, the what remains will be still of the form 2 power something. Similarly, A by 2 power n times B by 2 power m will be A B power 2 power n plus m. In this case, it is actually of the in the shortest simplest form, because A and B are odd, because these two are in simplest form. So, this is also, anyway, that is not important. The denominator is a power of 2, and even if you had to cancel, what remains will be a power of 2. So, this is in R. So, this is closed under addition closed under addition, closed under multiplication. So, R is a ring. So, I will leave the verification for you. R is a ring. So, these are some of the examples I wanted to do, which show that you have how to verify if a few given sets are rings or not. Okay. So, now to continue with the next problem, let us look at something about ideals. Okay. And this is something that is related to. So, this is the second problem. So, this is something related to homomorphisms and ideals. So, recall what is a group ring homomorphism. Let us say R to R prime is a ring homomorphism. So, let us say phi from R to R prime is a ring homomorphism, and recall what is the kernel. Kernel is the set of all elements in R which map to the 0 element of R prime, right. So, this is the definition of the kernel. So, and we know that it is what we call an ideal. So, the problem here is show that phi is injective if and only if kernel phi is 0. Okay. So, this I will remind you, if you have taken a course in group theory, this is exactly. So, this is a remark for you. This is exactly the same. This is exactly the same problem as in group homomorphisms. Okay. So, this is exactly the same problem as in group homomorphism. So, what I mean is, so let me write that here. If you have a group homomorphism, that also has the notion of a ring kernel. The group homomorphism happens to be a injective map if and only if the kernel is 0. And the reason that this is exactly the same is because whether something is in the kernel or not is really a group theoretic issue here, because it has nothing to do with the additive multiplication on R. It has everything to do with addition in R, and under addition R is a group, and whether phi is injective or not is purely a set theoretic property. So, let me quickly solve this problem. So, what is injective mean? So, I should probably remind you what is injective mean. Phi is injective definition, in case you forgot this. Phi is injective if two distinct elements go to two distinct elements. So, if phi of A is equal to phi of B for A B in R implies right. So, phi is injective if two elements of R map to the same element, phi of A is equal to phi of B, those two elements are equal to begin with. Okay. So, let us prove now. Suppose phi is injective. We want to show kernel phi is 0. Okay. So, so suppose, so first of all we know that phi of 0 is 0 because, okay, so I will simply write phi is a homomorphism, right. It is a ring homomorphism, so in particular it is a group homomorphism, and it sends the additive identity to additive identity. Now, suppose phi A is in the kernel of phi, then phi of A is 0, but 0 is also phi of 0 as I noted there. But now, since phi is injective, which is the hypothesis, and I recalled for you the definition of injective maps, phi of A is equal to phi of 0, that means A equal to 0. That means the only element of kernel phi is the 0 element, right. So, I have taken an arbitrary element of kernel phi and I have concluded that A is 0. So, that means kernel phi is equal to 0. Certainly 0 is in the kernel because phi of 0 is 0. So, kernel is just the 0 element, there is nothing else. So, now suppose kernel phi is 0, we want to show that phi is injective. Okay. So, this is also straightforward using the same ideas as before. Suppose we want to show phi is injective. So, assume or let phi of A equals phi of B. Okay, right. So, the definition of injectivity is if phi of A is equal to phi of B, we want to show A is equal to B. But if phi of A is equal to phi of B, so I will write it like this. By definition of ring homomorphism, I have this phi of A minus B is equal to 0, because phi of A minus B is phi of A minus phi of B, which is 0. That means A minus B is in kernel phi, which is again the definition of the kernel. If A minus B is in the kernel, I have assumed kernel is just the 0 element. So, A of B is equal to 0, that means A equal to B. So, this whole thing implies phi is injective. So, the problem is solved. I will only make the final remark that nowhere in this proof we have used multiplication on R. The fact that R is a ring which has multiplication is completely irrelevant for this problem. We only need a additive structure. So, we have shown that a ring homomorphism is injective if and only if its kernel is 0. So, we will use this problem in some special cases in next set of problems. So, I will end this video here today. Thank you.